All right, on to VSEPR. So VSEPR relies on this idea of steric number. And so uh, you just need to look at how many atoms are around your central atom, and then the trick is to how many lone pairs. This comes from doing the Lewis dot structure. And so in the molecule, this molecule, then SF4 in the formula, we don't see it. You have to do the Lewis dot structure, and then you would see you have one lone pair. So we have five things around it. All right, so that's the main thing. Once you have five things, now what we can use is this AXE tax method. So a refers to the central atom, and then X is the number of atoms around it. When we have a simple molecule like SF4, it's really easy. And then we can apply it to more complicated molecules and look at the fragments of it, and we'll get to that later. But for now, we're looking at determining it just from these simple ones. So like polyatomic ions and things like that. So now we know the number of E, so we have the steric number and X. And so then what we do is we start with these basic geometries. And this is what you first want to learn. And so if you have two things around it, we get linear. And then if we have three, then just think about starting with the linear and one comes up and you would have 90-degree interaction if it came here and 180. So it just wants to even them out. Remember, it's the valence shell electron pair repulsion. That's what's doing it. So it just wants to repel these electron densities so you get trigonal planar. And now when you bring in another one, a lot of times people think of an X and they want to cross, but it ends up if you came from this direction, you would see going three-dimensional. And so here you would have 90 between all these, and these are 120. You want to average it out to the same. So we get 109.5 tetrahedral. And so if you average 90 and 120, you get about the same answer. And so um, to get to this shape with the steric number 5, which is what we started with, now you just imagine starting with trigonal planar and you come from the top and the bottom, and those two forces cancel out, and we can easily see trigonal bipyramid. And here we see this is what's special. When we have 5, we have two different bond angles. We have 90 from the ones coming up on the bottom, and then 120 in the plane, just like we had here. And then when we have 4, then 4, 6, then we just go to that normal kind of thing with the like this in plane, and we have one on top, one on bottom, and everything's 90, so we get the octahedral arrangement. So that's what you first want to learn is the bond angles and the names for it. When you have just simple no lone pairs of electron, learn this first, and then you can move on to the next level. So the next level, now we start swapping out those some of those atoms with lone pair electrons. And so we have the same bond angles that we had here. It's just the geometry. You can't see this X here, so we just see the effect of it being bent. All right, tetrahedral, you don't see then the one coming up, so you see a trigonal pyramid. And remember, trigonal pyramid, really similar. So we replace the second one and we get bent again, just like this. Although this is a different angle, right? This would be 120 and this would be 109.5. And it would be less because those electrons are closer pushing it in, but you get the right ballpark. Okay, on 5, then because we have the different bond angles, when we put that electron on there, if we put it here, then it'll be interacting with 90 degrees with 3 different bonds. If we put it here, it only interacts with 90 degrees, 2 different bonds. So that's why it's lower energy shape being on that plane with the trigonal planar. It's kind of terrible because they rotate around, but hopefully you can see that. And then we place the second one, the same thing. It goes on that plane. And finally on the third. So third's easy. We get back to linear, but you wouldn't get that answer. Most people want to put it on the top here, all right? And so this is the hardest one. Save this for the last when you're learning it. And work on the others. The others are much more intuitive. So the first one, an octahedral, doesn't matter. We get the same answer wherever we put it. We put it here. We can see square pyramid versus trigonal pyramid. And but then when we put the second one, these want to be far enough away. If we put it here, we'd have 90-degree interaction. And by putting it here, we have 180. So that's why this is low energy state. All right, and so the last thing, I'll just switch over to fat. So if you go to fat VSEPR, then you can come in here and you can do the model, and now we can see. So we start with the linear, and we can add one, and you can see how it comes in at 90 and pushes down, and then you can show bond angle, show the geometries and everything. So I'm just going through the basic one. These have the same names, and then we'll come back and we'll do the other ones. So when I bring the fourth one in, this was really odd, but if you came in this way, hopefully you'd see it doing that 109.5. And you can rotate it around if you can't see it. So I don't know that that helps. But all right, so now we add another one and we can see trigonal pyramid. So the angles, it doesn't really show the 120 in there too well. But and lastly, octahedral, all 90 degrees. So now we can swap out, we can add a lone pair, and we can start to see then the names. And so square pyramid, then, and add another one, and wait, and we see square planar. All right. So uh, I really recommend like be able to do that. You can either memorize it or visualize it. Most people can tend to visualize it. And the cool thing is when you really know you have it, when you can just look, given the formula, kind of do the Lewis structure in your mind and do all of these. But you can easily draw it out to help you. I think that's everything I wanted. Yes.